Alright everyone, welcome to the second Physics QBit on constraint forces. In this video, we'll focus on understanding static friction as a constraint force and understanding how it's different than kinetic friction. If the phrase constraint force isn't familiar, check out the previous video, which is linked in the description, where we talk about what constraint forces are and work through a quick example with tension in a rope. Remember that there's two different kinds of friction. There's kinetic friction and there's static friction. Kinetic friction describes the frictional force between two objects that are moving relative to each other. So for example, you could imagine a hockey puck sliding across the ice. And static friction is the frictional force between objects that are stationary relative to each other, like a box in the back of a pickup truck. You might remember from class or your textbook that the formulas for these look pretty similar. In the kinetic frictional case, the kinetic frictional force is given by mu k times Fn, where mu k is the coefficient of kinetic friction, and Fn is the normal force. On the other hand, the static friction formula looks a little bit goofier. We have FSF is less than or equal to mu s times Fn, where mu s is the coefficient of static friction, and Fn is once again the normal force between the two objects. If you're a little confused by the less than or equal to sign in the static frictional force formula, you're not alone. In this video, we'll dissect how static friction works as a constraint force and what that weird less than or equal to sign means. Okay, remember, kinetic friction opposes any velocity at all and applies a force that tries to slow down the motion of the two objects rubbing against each other. This formula for kinetic friction is applicable in every situation when you have two objects sliding relative to each other. The kinetic friction depends on how sticky the surfaces are, given by this quantity, the coefficient of kinetic friction, and how hard you mash them together, which is given by this normal force between them. Static friction, on the other hand, tries to keep the surfaces from starting to move at all. That's why static friction is a constraint force. It's trying to keep the surfaces at rest relative to each other, just like how ropes and floors and tables try to prevent things from falling over and moving all the time. So let's look at a quick example problem. Imagine there's a heavy crate sitting on the ground. And let's say we're pushing on this crate, but it's not moving at all. Our goal is going to be to look at this situation and try to find the static frictional force between the crate and the floor. Let's start by using our usual four-step method for solving force problems by drawing a free body diagram. So as a quick refresher, we're going to start by drawing a free body diagram. We're going to translate that free body diagram into a set of Newton's second law equations. Then we're going to think about what constraints might be present in our system. And finally, we're going to solve whatever is at the very end algebraically to find the force that we want. So starting with our free body diagram, we see that this crate is on the ground, which means there's going to be a normal force from the ground pushing up on the crate. The crate's also going to be experiencing a gravitational force, Fg. We are pushing the crate to the right, and so there's going to be an applied force to the right. And because the frictional force is trying to oppose the motion of the crate, then the frictional force must point to the left in order to oppose our applied force. Because we can count the number of contacts being just our hands and also the floor, we know that our hands apply one contact force, the applied force, and because the floor contains surfaces that are touching the crate, there's going to be an upwards perpendicular force from the floor and a parallel force from the floor, accounting for the surfaces rubbing against each other. Then we can think of our one non-contact force for gravity, and we're pretty sure that our free body diagram is now done. Now we can move on to writing our Newton's second law equations. And what we're going to do is write one Newton's second law equation for each of the x and y directions independently. So in the x direction, we can see that we have two forces that make up the total force on this object. And there's going to be an applied force pointing to the right, so we'll start with a plus Fa. And we see that there's a static frictional force pointing to the left, so we have minus FSF. And because these are the only two forces in the x direction, then they must add up to the net force in the x direction, or in other words, the mass of the crate times the acceleration in the x direction. In the y direction, we see that we once again have two forces. We have a normal force pointing up, so we have plus Fn. We have a gravitational force pointing downwards, so we have minus Fg. And just like above, we know this must give the net force in the y direction, MAY. Okay, so just like before, what I'm going to do is pause here and ask you to think about the constraints. What is the constraint on the motion of our crate? Hopefully you said something like the crate is at rest. This is just like the problem we did before with the brick hanging from the ceiling. We know that because the crate is just sitting on the ground here, the acceleration in the x direction must be 0, and the acceleration in the y direction must be 0. And this lets us substitute these values into our Newton's second law equation to retrieve our simplified set of Newton's second law equations. In other words, Fa minus Fsf equals 0 for the x direction, and Fn minus Fg equals 0 for the y direction. Then we can recognize that if we want the static frictional force, all we need to do is just solve the first equation. And so solving the first equation, Fa minus Fsf equals 0, we can add the static frictional force to both sides and recover that the applied force is exactly equal to the static frictional force. If we consider that the object is too heavy to move, this makes perfect sense. The static frictional force is exactly enough to oppose any force that we apply. This is exactly what we saw in the case of the brick hanging from the ceiling as well, right? The tension was exactly enough to hold up the weight of the brick and nothing else. The important thing that we're trying to maintain here is that the crate remains at rest. The value of the static frictional force is whatever it needs to be to maintain that constraint. In this case, it's exactly equal to whatever force we're pushing on it with. In the last qubit, when we looked at the example of the brick hanging from the ceiling, we saw that hanging heavier and heavier bricks requires the tension in the rope to get higher and higher. There is a limit to this, however. If at some point our system demands that the rope needs to provide a constraining tension to an object that's too heavy, it snaps. We can figure out the breaking point of the rope by pulling on it with more and more force until it can no longer provide the force we're asking of it, and that's when the rope breaks. The same is true for static friction. This is where the formula for static friction comes in. The less than or equal to sign here tells us that as soon as you require that the static frictional force be larger than mu s times Fn, the object that it's trying to hold back will start to slide, and the static frictional force fails. This is exactly the same as a rope breaking or a table collapsing under an object that weighs too much. However, unlike ropes and tables, whose maximum forces you can only find through testing or experiment, the static frictional force has a limit you can actually calculate, as long as you know the coefficient of static friction. This is also a really good place to pause and revisit some of the differences between static and kinetic friction. Remember, kinetic friction only happens between surfaces that are moving relative to each other. As soon as the object starts to slide, then we know that the kinetic frictional force will always be exactly equal to mu kinetic times Fn. We can demonstrate this with a graph of the frictional force versus the force we push on the crate with. As we start off pushing harder and harder on the crate, the frictional force will increase in order to maintain the constraint that the object remains at rest. However, once we hit this maximum value where the frictional force is exactly equal to the coefficient of static friction times Fn, then the static friction will break just like a rope and apply no more force. At that point, the kinetic friction takes over and the object begins sliding. And now, as long as the object is sliding, the frictional force is exactly mu k times Fn, or in other words, the kinetic frictional force, and it remains this way until the object stops again. Note that the coefficient of kinetic friction, mu k, is always less than the coefficient of static friction. This is for reasons that are both neat and also outside the scope of this video, but what this means for us is that as long as an object overcomes static friction, it will begin to slide and be only under the influence of kinetic friction. Okay, we just went through a lot. Let's summarize really quick what we learned today. First of all, there are two kinds of friction, kinetic and static. Kinetic friction is the force between objects that are moving or sliding relative to each other. On the other hand, static friction only keeps surfaces from starting to slide relative to each other. We have a formula that always works for kinetic friction, but static friction is a constraint force, just like the normal force or the tension force. Just like normal forces from tables or tension forces from ropes, the static friction can be anything below a particular maximum value, expressed by the less than or equal to sign in the formula. Once your constraint demands that the static friction needs to be stronger than this maximum value, the static friction snaps like a rope and the system will start moving and being subject to only kinetic friction. Alright, that's all I have for static friction today, and I hope this discussion helped you understand static friction as a constraint force a little better. As usual, if you have any questions, please feel free to leave them in the comments and I'll try to answer them if I can. If you want to see some example problems focused on static friction as a constraint force, check out the office hours video linked in the description. Please like and subscribe for more physics problem solving tips and tricks. This has been Physics Tutoring Quantized.